Hello there. Today I will be discussing some college basketball statistics that I have done some heavy research on over these past several weeks. I used a data site known as KenPom, which is heavily used and referenced by many basketball analysts and coaches throughout their seasons. And it deals with all types of team statistics such as offense and defense and the pace they play at and their strength of schedule. And I'll soon be discussing with you some of these variables. Now for my research, I used the 2018-2019 season as my reference, which was the most recent full season played, thanks to COVID-19. Now the two main research questions I had go pretty much hand in hand with each other. The first question, what variables have a significant impact on a college basketball team's winning percentage? Well, I made the null hypothesis for that, where all the betas would equal 0 for the model, so that none of the predictors actually have an impact on the win percentage. Now for the second research question, which model would be the best for predicting a college basketball team's winning percentage, I made HO that the first order model will suffice in predicting, and that none of the beta k's would have to be dropped from the model, no transformations would have to be made, and etc. Now the data can be found in the link below, and if you go to the data, I'd like to point out that I only used the first 150 data points for this research, and I also changed the win-loss record to winning percentage because it's easier to make a model off of that. So from the research questions, you can see that win percentage will be used as the response variable. Now I used 6 explanatory variables in this first model. Offensive rating, which is measured by the points scored by a team per 100 possessions or per the 100 times that they have the ball. Defensive rating, which is points allowed per 100 possessions. The tempo, which is the amount of possessions a team has for a whole game, and in college basketball that is 40 minutes. The opponent's offensive rating, which is the average offensive rating for the opponents of the team. And opponent's defensive rating pretty much uses the same thing except for defensive rating. And conference, which is a categorical variable, where I took major conferences like Purdue, which is in the Big Ten, so they are in a major conference. I used them as a 1, and then teams that are in a minor conference, I added them as a 0, so these are usually smaller schools. Now, as previously said, I went with 150 college basketball teams because the original data set had 353, but a majority of them are from minor conferences, so it would kind of skew the data a little bit if I kept all 350. So having 150 pretty much made it more even between the major and minor conferences. Now the explanatory variables were chosen from the data set as variables that logically made sense, because in the data set there's also variables like luck, which would be kind of cool to measure, but it wouldn't make, I don't know how they exactly measured luck as a statistic, so it really wouldn't apply to this model very well. Now, in order to answer the research questions, the first thing that needs to be done is a preliminary analysis on our data. So in the residual plot, you notice that there is a slight curve which indicates that there could be some constant variation issues, but it's not a huge significant curve, so we can't conclude anything yet. And the same can kind of be said about the normality plot. There are outliers, like you can see towards the bottom and top, but like we said, that you can't really conclude anything just yet since it's just a preliminary analysis. Now for the box plots, there does appear to be some outliers in the offensive rating and the tempo, but whether these points are influential or not, we do not know. So it's possible that we could just ignore these points. Now in the correlation plots, it mostly looks okay, except between the relationship between opponent's offense and opponent's defensive ratings. There definitely appears to be a linear relationship there, so there easily could be some multicollinearity, but further examination is required to see if any remedial steps are necessary for our data or model. So to test for constant variance, the Brown-Forsyth test was used in R, and based on the result, it does appear that their constant variance is not really violated. Now, the same cannot be said for the Shapiro-Wilk normality test, which, hence the name, tests the normality of the errors. Now the p-value is 0.04612, and the default R alpha is 0.05, so the p-value is less than alpha. Now, however tempting it might be, even though it's just slightly less than alpha, remedial measures probably should still be taken, and maybe a transformation will help make the p-value greater than alpha. As for the added variable plots, it is noticeable that the conference of a certain team shows that it might contain very little information that's useful for predicting that team's win percentage beyond what is contained in the other variables. The same cannot be said for the other variables, except tempo might not have too much of an impact, but it's definitely more of an impact than conference. Now for the influential plot, there definitely does appear to be vertical and horizontal outliers, but a lot of them, the areas of the circle, appear to be small, so that means they're not that influential. But if you look at number 2, which is towards the bottom right corner of the influential plot, that is a pretty big circle, so it is likely that is an influential point. Now, if you are a follower of college basketball, you might be able to guess what team that is, and it's Gonzaga, which is a team that is known for always having a good offense and defense, but their opponents' offenses and defenses based on their schedule are usually pretty weak. So it is pretty predictable that they would be an outlier in this model. As for the DF betas plots, it is pretty obvious that there are some influential points because the 2 divided by the square root of n comes out to be 0.1633, so any absolute value that's greater than that in the plots is considered to be influential, and there are some to be seen in most of these plots, so remedial measures will definitely have to be taken, possibly robust regression, and we will see what that does. So to validate my suspicion that conference could be dropped from the model, I performed a stepwise regression model in R, and it indeed said that conference could be dropped safely. And you can also see this in the best subsets algorithm here. You can see in the highlighted terms that model does not contain conference. And you see there are also 2 models it could potentially suggest, but I went with model 5 simply because, well, for one, model 4 only has one lowest term in SBCP, and also the stepwise regression model did not suggest that dropping tempo would be a good idea, so that's why I went with 5. Now the remedial measure I took to fix normality was I decided to transform y, and this is mostly due to the residuals not being normal. And I decided to square it, and it took me a few steps to figure this out, but I decided to go with the shape of the variable versus predictor plot. I left all the explanatory variables unchanged as I didn't see any need to transform those. Now, to lessen the impact of the influential points, I went with robust regression. And once applied, you can see based on the OLS in the new estimate that it reduced the weight of both the tempo and the opposing defensive rating. So, and we will see later how that affected the model. And so, like I said earlier, that there appeared to be some multicollinearity issues. But when I ran the tests, it said that all the variation influential factors were less than 10. And so that indicated, if they were greater than 10, obviously the multicollinearity would be a real big issue. And none of the R-squares were above 0.9. And I went ahead and did a ridge regression on this to verify this, and it indicated that the model that performed best in cross-validation used a lambda equals 0, which means that transforming the model to fix multicollinearity would probably make a worse model. So it was safer to just avoid that remedial measure. So after the remedial measures were taken, I decided to run another diagnostic test on the model. So the Brown-Forsyth test, which tested for constant variance, still looks good. Now the Shapiro-Wilk test, which showed that normality was an issue last time, found that the p-value is now greater than R's default alpha of 0.05, meaning that the non-normality issue seems to have fixed itself once the model was transformed from y to y squared. The added variable plots pretty much look the same, so no worries there. The DEF betas plots, which show that there were some really influential points in the model, well, it looks like their impact has been shrunk thanks to the robust regression. Now they're not perfect because there are still some that are greater than that 2 divided by the square root of n value I showed you earlier, but nonetheless this is a much more improved model. Now the k-fold cross-validation was run with k equals 10, and as you can see for the new model, which is at the top compared to the bottom model, and I'm like to point out they're both squared, the RMSE and RMSE is smaller for the newer model and the R squared is greater, so it looks like this model is improved. And as you can see at the bottom, there's the final model that I have gone with. So as previously discussed, the normality and the influential points found in the preliminary analysis showed that these were the main issues with the first order model, and these were fixed with using robust regression to dampen the influential points and using a Box-Cox transformation for transforming the y variable win percentage to y squared. Now for the second research question, we definitely reject the null hypothesis based upon the stepwise and best subsets algorithm, which showed that the categorical variable conferences was not really needed to predict win percentage. So beta 6 could be dropped, meaning that not all betas were significant in determining win percentage. Now, based on the ANOVA results, we can conclude, we can make an analysis for about the first research question, as we see that all the p-values are less than 0.05, so we can reject the null hypothesis and conclude that these variables have a significant impact on win percentage. Now, based on the p-values though, we can pretty much say that offensive rating, defensive rating, and the opponent's offensive defensive rating definitely play a significant factor in determining the team's win percentage. Now the tempo they play at, it looks like there is an impact, but calling it significant might be a little too much since the p-value is pretty large, even though it is less than 0.05. Now, this model, like I said, is not perfect. It's just an improvement over the first model in predicting what affects a team's winning percentage. Other factors like home and away, the amount of home and away games teams have, or like the injuries a team could suffer through a season, or the team's free throw percentage, well, these are not really measured by KenPom, and these could definitely still have a factor on how many games a team wins based on their win percentage. So the model's ability to project winning percentage is not perfect, but if you're just looking at these variables in particular, it does show what is important in determining the response variable.